Okay, next let's have a look at the concept of continuity, which is also related to limits. So the graph shown here in figure A represents a continuous function. Geometrically, this is because there are no jumps in the graphs. That is, if you pick a point on the graph and approach it from the left and right, the values of the function approach the value of the function at that point. For example, we can see that this is not true for function values near x equals 1 on the graph in figure B, which is not continuous at that location, right? So how do we define continuity of a function at a certain point? This is the definition of a continuity of function at a certain point. A function fx is continuous at a point x equals a if the following three conditions are all satisfied. First, fa is defined. Second, the limit of fx when x approaches a exists. And third, the limit of fx as x approaches a should equal the image of that function at x equals a. And graphically, you can think of a continuity as being able to draw your function without having to lift your pencil off the paper. If a pencil has to jump off the page to continue drawing on the function, then the function is not continuous at that point. So here are some examples where at a certain point the function is continuous or not continuous. So if you look at the first graph here, for all of the graphs here, we consider the point when x equals a. Okay, so for the first diagram here, as you can see, f is defined, right? And then we know the limit of fx when x approaches a exists. And also we know the limit of that function when x approaches a also equals the image of that function at x equals a. So all of the three conditions can be met. So this function is continuous at x equals a. Did you get it? If you consider the second diagram here, when x equals a, first of all we know fa is not defined. So the first condition cannot be met. So this function is not continuous at x equals a, right? Then if you consider the third diagram here, first fa is defined, which is this point here. Second, the limit of fx when x approaches does not exist because we know the left side limit does not equal the right side limit for this function at x equals a, right? So the second condition cannot be met, then we can say the function is not continuous at x equals a. Then for the last graph, first of all, fa is defined. Second, the limit of x when x approaches a equals that point here. So the second condition can also be met, but the third condition cannot be met because we know fa is here, but the limit of fx when x approaches a is here. They do not equal. So the third condition cannot be met, and we can also conclude the function is not continuous at x equals a. Are you clear? Okay, so if you know the continuity of a function at a certain point, then we can also define the continuity of a function on an open interval, because both of the two endpoints are so special. For example, the left endpoint only has a right limit, and the right endpoint only has a left limit. So first we exclude the two endpoints and have a look at the continuity of a function on an open interval. A function f is continuous on an open interval a, b if it's continuous at every point in that interval. Furthermore, a function is anywhere or everywhere continuous if it's continuous on the entire real number line from negative infinity to positive infinity. You get it? Okay, next let's have a look at an example to illustrate this concept, the continuity of a function. We can draw this function without lifting our pencil, except at these points, x equals -5, x equals -2, x equals -1, and x equals 4. Thus, fx is continuous at every real number except at these 4 numbers. At these numbers, x equals -5, -2, -1, and 4, the function fx is discontinuous. You see that? And at x equals -2, we have removable discontinuity. So we have different types of names to name different types of discontinuity. At x equals 2, we have a removable discontinuity because we could remove this discontinuity simply by redefining f -2 to be 3.5. Formally, we say fx has removable discontinuity at x equals a if the limit of fx when x approaches a exists but is not equal to fa. Okay, so that's the meaning of removable discontinuity. Also note that we do not require fa to be defined in this case. That is, a need not belong to the domain of fx. At x equals -5 and x equals -1, we have jump discontinuity because the function jumps from one value to another. From the right of x equals 4, we have infinite discontinuity because the function goes off to infinity. These types of discontinuities are summarized below. We have removable, jump, or infinite discontinuity. For removable discontinuity, basically we have the limit of fx when x approaches a does not equal fa. For jump discontinuity, the limit of fx when x approaches a from both sides does not equal. For infinite discontinuity, we have either limit of fx when x approaches a from positive side equals either positive or negative infinity, or you could also have the limit of fx when x approaches a from the negative side equals positive or negative infinity. You get it? Alright, let's have a look at an example to check your understanding. So suppose we have a function whose graph looks like this. State the domain of this function and then evaluate each of the following expressions. And is the function continuous or discontinuous at x equals 1? State the type of discontinuity if applicable. So I'll give you 2 minutes to consider this question, and then we'll have a look at the solution together. Okay? Okay, let's have a look at the solution together. So first, the domain of this function is whole real number set, right? And second, we can easily evaluate its left limit at x equals 1, the right limit at x equals 1. Apparently they are not equal. So we do not have a limit when x approaches 1. But the graph tells us that f1 equals -2, right? So even you put this point back, you do not have a continuous function at x equals 1. And its left limit does not equal to its right limit, so the type of discontinuity is called a jump discontinuity. You get it? Okay, then let's have a look at another example. Examine the given graph and answer the following questions. Again, I'll give you 2 minutes to think about this question. Alright, so this is the solution of this question. First of all, the domain is x belongs to a real number set, but x cannot equal 4. And then we can easily see the left limit and the right limit of that function at x equals and when x approaches 4 is negative infinity on the left side and positive infinity on the right side. They do not equal, so the limit when x approaches 4 does not exist. And also f4 does not exist either. Since this function y value is either increasing or decreasing without this function is undefined at x equals 4, right? Since y value is either increase or decrease without bound as x approaches 4, this function is said to have a infinite discontinuity at x equals 4. You get it? Okay. And another question. Another example. Can you examine the given graph and answer the questions below? Alright. Then first, the function is defined for all values of x. So the domain is just a real number set. And we can easily find its right limit is 0 at x and at when x approaches 0 from the positive side, and when x approaches 0 from the negative side, the left limit is 0. And of course, the limit when x approaches 0 of this function is 0 as well. And also we know the image of that function when x equals 0 is also 0. So all of that three conditions can be met at x equals 0. So this function is continuous at x equals 0, right? Alright, so if you don't have any question, next let's have a look at the concept of one-sided continuity of a function at a point. A function f is left continuous at a point a if the limit of that function when x approaches a from the negative side equals fa, and the right continuous at a point a if the limit of that function when x approaches a from the right side or positive side equals fa. If a function f is continuous at a, then it is both left and right continuous at a. Also, the above definition regarding left or right continuous functions is illustrated with the following figure. So, for example, if you have a function shown on the left side, we have the left side limit of that function when x approaches a from the left side equals its image when x equals a, right? So we can call this function is left continuous at x equals a. And also this is in accordance with what is shown here. Function is left continuous. And for example, if you have a function shown on the right side, then when x approaches a from the right side, the limit of fx equals fa, right? In that case, we call it right continuous at x equals a. You get it? Okay, so now we can define the continuity of a function on a closed interval. The one-sided limits allow us to extend the definition of continuity to closed intervals. The following definition means a function is continuous on a closed interval if it's continuous in the interior of the interval and possesses the appropriate one-sided continuity at the endpoints of the interval. The function f is continuous on a closed interval ab if all of the three conditions can be met. First, it's continuous on the open interval ab. And then we can consider the one-sided continuity on both ends, right? And second, it is right continuous at point A, which means the limit of fx when x approaches a from the right side equals fa. And third, it's left continuous at point B, which means the limit of that function when x approaches b from the left side equals fb. This definition can be extended to continuity on half-open intervals such as a to b, left side open, right side closed, or a to b, left side closed, right side open, and unbounded intervals such as greater than or equal to 0 or less than or equal to 4, and etc. Did you get it? Another example to check your understanding. So the function here shown on the left is continuous on the following intervals. First, from A to B, left side closed, right side open. And then from B to C, also left side, so this time left side closed, right side closed. And it's continuous on the interval C to D, left side open, and right side closed. It's continuous on the interval d to e, both sides open, and it's continuous from e to cos infinity, left side closed. Any questions? Alright, next. Here are the common functions that are known to be continuous. Again, I'm not going to prove this for you here, but it's better to know all of these functions are continuous at some intervals. All elementary functions are continuous at any point where they are defined. An elementary function is a function built from a finite number of compositions and combinations using 4 operations, namely addition, subtraction, multiplication, and division, over basic elementary functions. And also we have the following functions which are basic elementary functions. You can have a look at that by yourself. Okay? Alright, let's have a look at some examples. First, polynomial functions are continuous everywhere, namely at every real number. Second, rational functions, px over qx, where px and qx are both polynomials, are continuous at each point in their domain, that is, except where qx equals 0. The function fx equals 1 over x, for example, is continuous except at x equals 0, okay? Where f is not defined. Next, the absolute value function, fx equals absolute value of x, is continuous everywhere. Next, trigonometric, inverse trigonometric, exponential, logarithmic functions are continuous at each point in their domain. Functions of the type nth root of x, where n is a positive integer which is greater than or equal to 2, are continuous at each x for which the nth root of x is defined. Last example, the greatest integer function, fx equals greatest integer that is less than or equal to x, is discontinuous at each integer since it does not have a limit at any integer. Are you clear? Okay, next there is a theorem on the continuity of a function you should know. First is the extreme values theorem, which states that if f is continuous on the closed interval a to b, then f attains a minimum value and maximum value somewhere in that interval. Okay, number 2, the intermediate value theorem. If f is continuous on a closed interval ab, and m is a number such that m is somewhere between fa and fb, or m is greater than or equal to fa and less than or equal to fb, then there is at least one number c in the interval ab such that fc equals m. Note that an important special case of the intermediate value theorem states that if f is continuous on the closed interval ab and fa and fb have opposite signs, then f has a 0 in that interval. There is a value c in the interval a to b where fc equals 0. Alright, next one, the third theorems. The continuous functions theorem. If functions f and g are both continuous at x equals c, then so are the following functions. All of the following functions are also continuous. A constant function. A constant theorem. If you use a constant number k times fx, then k times fx is also continuous. B, the sum of these two functions are also continuous. C, the differences between these two functions are also continuous. D and E, the product and quotient of these functions, as long as the denominator is non-zero, are also continuous. Okay? And number 4, the composition of continuous functions theorem. If the function g is continuous at x equals c, and if the function f is continuous at x equals gc, then the composite function f of g of x is also continuous at x equals c. Are you clear? All right, if you're already clear with this, let's have a look at an example to check and understand. Can you show that fx equals x squared minus 5 over x plus 1 has a root between x equals 2 and x equals 3? So we can consider this problem using the theorem we have learned here, right? The rational function f is discontinuous only at x equals -1. And then we can check their image at x equals 2 and 3 respectively. We know f2 will give you -1/3 and f3 equals 1, right? Since f is continuous on the interval 2 to 3, closed interval, and f2 and f3 have opposite signs, there is a value c in the interval where fc equals 0. Can you see that? By the intermediate value theorem. Okay, let's have a look at another example. Also note that if we already know a function fx is continuous at a point x equals a, then this can help us to find the limit of that function when x approaches a, right? So basically, if you know the function is continuous at that point, then we have the limit of that function when x approaches a should equal fa, right? So using this, can we evaluate the limit of that function when x approaches 2? Okay, let's have a look at the solution. So first of all, we know this is a polynomial function. Polynomial function is continuous anywhere in its domain, right? So apparently this function is also continuous at x equals 2. So we can use this property to help us to evaluate that. So basically the limit of that function when x approaches 2 should equal the image of that function when x equals 2, right? Therefore that equals 3 times 2 to the power 4 minus 5 times 2. And that gives us 3 times 16 minus 10. Eventually we have 38, right? Okay, however, sometimes we can not just insert the value into the original function to evaluate its limit. So let's have a look at some examples. Suppose we have 3 expressions like this. Can you evaluate their limits? Okay, let's have a look at the solution. So first of all, you can just insert x equals x to that rational function, right? But when x approaches positivity, that means x cannot be 0. So we can divide both sides of the numerator and denominator with an x, or sometimes x squared. So for example, if we divide both of them using x, then we will have 3 over x minus 1 here, right? And then 4 over x plus 1 plus x. So when x approaches positive infinity, this part will approach 0, right? And this part is -1, so the numerator will approach -1, right? But the denominator will approach, well, there are 3 parts. When x approaches positive infinity, we know this part will approach 0, this part will approach positive infinity, this part is fixed, which is 1. So the denominator will approach positive infinity, right? So the entire expression will approach 0. Can you see that? A fixed number 1, a number will approach, that will approach -1 over the number which is approaching positive infinity will approach 0, right? Okay, so we can do the same thing for the second expression. We can divide both sides using either x to the power 4 or x to the power of 3. So for example, if we divide both the numerator and denominator using x to the power 3, then we have 4x plus 5x squared plus 1 over x to the power 3. And then we have 37 minus 9 over x to the power 3. When x approaches positive infinity, this part will approach positive infinity. This part will approach 0. This part will approach 0. Right? So your numerator will approach positive infinity. And your denominator will approach 37. It's a fixed number, 37. So a positive infinity over 37 will approach positive infinity, right? And that's its limit. You see that? How about the third one? You can divide both sides using x cubed, right? Then we can easily evaluate its limit is negative 1 over 2. Any questions? Okay, let's have a look at the rational function theorem. If the degree of px is less than that of qx, then we have the limit of px over qx when x approaches positive infinity equals 0. If the degree of px is higher than that of qx, then the limit of px over qx equals positive infinity or negative infinity when x approaches positive infinity. So in that case, the limit does not exist. And if the degree of px and qx are the same, then the limit of px over qx when x approaches positive infinity equals an over bn, where an and bn are the leading coefficient of the highest powers of x in px and qx respectively. So this is the main takeaway of the previous example we have talked about. Again, here I'm not gonna prove this for you. Just remember, it's a rational function theorem. If you have a rational function, then you could apply this theorem to help you solve questions. Okay. Also, this theorem holds also when we replace x approaches positive infinity by x approaches negative infinity. Okay. Note that also when the limit of px over qx equals 0, when x approaches to both positive or negative infinity, then y equals 0 is a horizontal asymptote of the graph of y equals px over qx. And also when the limit equals positive infinity or negative infinity, when x approaches either positive or negative infinity, then the graph has no horizontal asymptotes. When the limit of the function equals an over bn, when x approaches positive or negative infinity, then y equals an over bn is a horizontal asymptote of the graph of this function. Okay? Alright, again, let's have a look at some examples to check your understanding. Okay? So consider these 5 questions. Are you able to evaluate the limits of these questions? Let me know if you finish. Okay. Okay, let's have a look at the solution together. Alright, so we have talked about that the limit of a rational function when x approaches either positive infinity or negative infinity is related to the ratio of the two highest order terms, right? So in this case, x cubed is higher than x squared. So when x approaches positive infinity, the limit of this rational function is 0, because x cubed is a higher order infinity than x squared, right? Or the ratio between these two terms is 100x squared over x cubed. This will give you 100 over x. When x approaches positive infinity, this will give you 0, right? Okay, so next one. X cubed over x squared is x. When x approaches positive infinity, this will give you positive infinity, right? Oh, sorry. It says when x approaches negative infinity. So this will give you negative infinity. Because when x approaches negative infinity, this part will approach negative infinity. This part will approach positive infinity. The ratio between this part will approach negative infinity. Well, the ratio between this, the quotient between these parts is x, right? When x approaches negative infinity, the limit of x is negative infinity, not positive infinity. So there is no limit. Or you could also say the limit is negative infinity. Next one, the ratio between the two highest part is x over 5x, which is 1/5. So when x approaches positive infinity, this will give you 1/5. Next one, highest order of the term is negative 3x cubed over 7x cubed. So when x approaches negative infinity, the ratio between these two polynomials will approach negative 3 over 7. Next one, x cubed over negative x squared is negative x. When x approaches positive infinity, this will approach negative infinity, right? Sometimes we might have limits that involve a indeterminate form. For example, how do you evaluate the limit of this rational function when x approaches 1? I'll give you some time to consider this problem, and we'll have a look at the solution together, okay? Okay, so at first glance, you might want to insert x equals 1 into the rational equation, rational expression. But if you insert x equals 1, you will end up like 0 over 0. And we don't know the limit when you have a 0 over 0, right? So if you have an expression like this, well, usually we can simplify that first. So that equals the limit when x approaches 1 of x minus 5 times x minus 1 over x minus 2 times x minus 1. So x approaches 1 means x is a number close to 1, but never 1 itself, right? X is not a number to 1, but a number close to 1. So we can safely cancel these two terms. So that gives us limit of this expression when x approaches 1. And therefore now you can insert x equals 1 there, because we know rational function is continuous anywhere when it's defined. So that gives us 1 minus 5 over 1 minus 2, which is 4, right? Okay, now let's consider another problem. This time it's your turn to solve this question. So the limit of this rational function when x approaches negative 3. Okay, let's have a look at the solution together. Again, if you substitute x equals 3 to the rational expression, you will end up like 0 over 0. It's not feasible to find its limit, right? So we can expand the numerator and simplify using factoring to remove the indeterminate form. So the original expression can be simplified to x plus 3 times x minus 1, then divided by x plus 3. So x approaches negative 3 means x is a number close to negative 3, but never reaches negative 3. So x plus 3 is not a number that equals 0. So we can safely cancel these two numbers. So basically you are evaluating the limit of x minus 1 when x approaches negative 3. And this is a linear function. It's continuous anywhere in its domain. So the limit of this function when x approaches negative 3 equals negative 4. Now you can insert x equals 3 to that expression, right? Did you get it? Okay, and next let's have a look at another example. Can you evaluate the limit of this expression when x approaches 0? Okay, so substituting x equals 0 will result a 0 over 0. We cannot evaluate its limit, right? However, we cannot factor in this case, so we have to use a different method of finding the limit. We can try to rationalizing either the numerator or the denominator. In this case, we can try to rationalize the numerator. So we can multiply both the numerator and denominator with this expression. And then your numerator becomes square root of 4 plus x squared minus 2x. And your denominator is x times square root of 4 plus x plus 2, right? And then simplify that will give you x over x times square root of 4 plus x plus 2. So x can be cancelled with x here. And then when x approaches 0, this function will approach 1 over 4 plus 0 plus 2, which is 1 over 4. Did you get it? Alright, next let's have a look at some properties of limits. So these are the commonly used properties of limits. You can use them to help you find the limit of a given function. So let's briefly go over all the properties here. First, the limit of a constant is equal to the constant. So the limit of a constant number c when x approaches the number a is always the constant itself. Did you get it? For example, if you have a limit of a number 7 when x approaches 1, this limit is this constant itself, because no matter what x is, the limit of a constant number is always itself. Did you get it? The choice of x does not affect the limit of a constant number. Secondly, the limit of x as x approaches a is equal to a. Because this is a linear function, we know this function is continuous anywhere in its domain. So the limit of this function when x equals a specific point should equal the image of that function at that point. Third, the limit of the sum of two functions equals the limit of the first function plus the limit of the second function. And this is also true if you change the plus sign to minus sign here. And number 5, the limit of a constant times a function is a constant times the limit of the function. We can put the constant number c in front. Next, the limit of the product of two functions equals the product of the limits of the two functions. And this is also true if we change the multiplication sign to division sign. So number 7 is also true. And the limit of a power is the power of the limit, provided that the exponent is a rational number. The limit of a root is the root of the limit, provided that root exists. Number 10. Limit of composition. Suppose that the limit of gx when x approaches a equals L, and the limit of fx when x approaches L equals FL. Then the limit of f of g of x when x approaches a will give you FL. And last property is the limit of a composite function, which states that the limit of a composite function is the composition of the limits, provided the outside function is continuous at the limit of the inside function, which also means the limit of f of g of x equals the limit of f of g of x when x approaches c, which gives you f of the limit of gx when x approaches c, if f is continuous at the limit of gx when x approaches c. Also note that for all the properties here, we assume that the limit of fx when x approaches a and the limit of gx when x approaches a exist, and c is any constant. And property number 12, the squeeze or sandwich theorem, which states that if fx is less than or equal to gx, which is less than or equal to hx, and if we have the limit of fx equals the limit of gx when x approaches c, which both equals L, then we also have the limit of gx when x approaches c equals L. Well, this concept can be illustrated using the following diagram. Alright, let's see an example to check your understanding of these properties. Given that the limit of fx equals 3 when x approaches 2, the limit of gx equals 4 when x approaches 2, and the limit of hx equals 5 when x approaches 2, can you evaluate the following expression? The limit of fx times gx plus hx when x approaches 2. Alright, let's have a look at the solution. So we know the limit of the sum of the two functions equals the limit of the first function plus the limit of the second function when x approaches the same number. And also we know the limit of the product of two functions equals the limit of the first function times the limit of the second function, then plus the limit of the, well, you can copy the rest of the expression here. So that means we need to find the limit of the first function when x approaches 2, which is 3, then times the limit of gx when x approaches 3, plus the limit of hx when x approaches 2, which is 5. And therefore we have 17, right? Any questions? No? Okay, so next let's have a look at some other basic limits. These are the commonly used basic limits. I hope you can memorize their result. The basic trigonometric limit is the limit of sine theta over theta equals 1 when theta approaches 1, if theta is measured in radians. And the limit of sine x over sine x when x approaches positive infinity equals 0. Well, we can easily prove this by using the following analysis. You can have a look at this by yourself. Or actually, you can also use this diagram to help you memorize. So suppose we have a 2D Cartesian plane, and then we have, for example, a unit circle whose radius is 1. Then suppose we have a angle theta here. When theta approaches 0, that means, well, first of all, we know theta equals the length of this arc, right? Because you have a unit circle and this angle is theta, so we know the length of this arc is theta. And sine theta is the y coordinate of this point, because the coordinates of this point is cosine theta, sine theta, because this is the intersection between the unit circle and the terminal arm of an angle theta, right? When theta approaches 0, of course, the y coordinate of that point should equal the length of that arc. So the ratio between these two quantities should approach 1. You get it? And you can easily prove the other expression as well. Okay, let's see an example to check your understanding. Can you evaluate the limit of this ratio when x approaches 0? Well, we know that the limit when x approaches 0 of sine x over x will give us 1, right? But here, these two inputs are not equal. We have a 3x in the numerator and x in the denominator. So first of all, we need to convert them to some equal quantities. So this equals the limit of sine 3x. We can multiply both sides of the numerator and denominator with a number 3, right? And therefore, this equals the limit of, well, when x approaches 0, this is equivalent to, say, 3x approaches 0, right? So this will give you the limit of 3x equals approaches 0 of 3 times sine 3x over 3x. Of course, if you have a constant number here, you can put it in front. So that's 3 times the limit of 3x approaches 0 sine of 3x over 3x. So you can consider 3x as u. When the input when the input u approaches 0, sine u over u will approach 1, right? Therefore, the final result is 3. You see that? Okay, let's have a look at another commonly used basic limit. The number e can be defined as follows. E equals the limit of this expression when n approaches positive infinity. The value of e can be approximated on a graphing calculator to a large number of decimal places by evaluating this expression for large values of x. Again, I'm not gonna prove this property here for you. Well, actually, people already proved this expression has a limit when n approaches positive infinity, and then we use a special letter e to denote the limit of this expression. So here, I'm not gonna prove that why we have a limit for this expression when n approaches positive infinity. If you are interested, you can just let me know after this class. We'll talk about that after this class, okay? So far, as long as you know e is defined in this way, you should be fine. Okay, let's see an example. So suppose you already know that the limit of this expression exists, and we use letter e to denote the limit of this expression when n approaches positive infinity. Can you prove that the limit of this expression when n approaches negative infinity also equals e? Okay, we can actually prove this in the following way. So basically, you can let m equals negative n, right? Then n approaches negative infinity is equivalent to m approaches positive infinity. And then we can rewrite the expression to 1 minus 1 over m to the power of negative m, and transform that to the limit of this expression when m approaches positive infinity, and detach this expression into two parts. The first part is 1 plus 1, second part is 1 over m minus 1, and then raise to the power of n. And this equals limit of m minus 1 approaches positive infinity, because m minus 1 approaches positive infinity is equivalent to m approaches positive infinity, right? And the expression can be expressed as 1 plus 1 over m minus 1 to the power of m minus 1 multiplied by another 1 plus 1 over m minus 1. So we already know the limit of the products of two functions equals the limit of the first function times the limit of the second function. The first limit, we have already learned this actually is e, right? You can consider m minus 1 as your independent variable x. So the limit of this expression 1 plus 1 over x to the power of x when x approaches positivity will give you e, right? And for the second expression, when m minus 1 approaches positive infinity, this part will approach 0. So that limit will equal 1. So eventually you have e times 1, which equals e. Therefore, we know for both n approaches positive infinity or negative infinity, the expression 1 plus 1 over n to the power of n always equals e. Okay, I hope you can put this down on your notebook and memorize it by yourself. Okay.